Okay, let's start class. I think we stopped here in last class, so let's continue. So we talk about the uh, association rule mindings, and last time we showed we can use the graph-based visualization tools to see the relationships among a few rules. Okay, so here the rules is as vertices, and we have the arrows pointing to the vertices. These are the uh, antecedents, and for those arrows point out of the uh, vertices, these are the consequent. And we see for these rules, some of the items are the consequence of a rule, but an antecedent of another rule. So there are some connections. It's like a network. But this approach is limited by the number of rules. If you have over, let's say, 100 rules, it doesn't work because it's too complicated and it's hard to see. So for many rules, we can use a different tool, that is the grouped matrix plot. So the grouped matrix plot is still using the plot function, but the method is grouped. Okay, so here we lower the confidence interval from 0.8 to 0.5 so that we will have more rules. Okay, but the support threshold is still 0.1%. So we have this group matrix plot for over 5,000 rules. Now we have over 5,000 rules. Okay, and here the size of the bubbles is proportional to the support for the rules, and the color, the darkness for the bubbles is proportional to the lift. Remember the lift? Lift, if it's independent between the antecedent and the consequent, then the lift should be around 1, right? If the lift is much larger than 1, that means there is a strong association between the right hand side, which is the consequent, with the left hand side, which is the antecedent. Okay, so here you can see, look at the size and the darkness. We are interested in this bubble because this bubble has pretty large support. That's good. And also you can see the darkness. So the lift size for these is very high compared to the others. So what does that mean? So this means if you go to the top row, so you will see a number. So there's a 3. 3 means what? So 3 means we have 3 rules contained in this bubble. So we have 3 rules. Okay, and then in the parentheses you will see we have the instant food products plus 2. So that means what? So that means so for all these 3 rules, they all have the common item in the left hand side. Remember, left hand side is the antecedent, and that item is the instant food products. Plus 2 means we have 2 other items in the left hand side, in the antecedent. Okay, but the right hand side, that's the consequent, are the same. So if you move to the left or right column, you will see the hamburg meat. So these 3 rules, which have large support and relatively high lift value, that means a strong connection between the right hand side and the left hand side, they have the same consequent, is the hamburger meat, but they have the one common item for the antecedent, which is the instant food products, and plus 2 others. Okay, so this is how you read the group matrix plot. And you can also interpret in a similar way for other bubbles. Okay, so this is a very useful tools for uh, visualizing many tools or many rules. This is the example 2. So example 2 here is a Titanic data set. We have 4 categorical variables: class, sex, age, and survived. So here, I just run the a priori on the Titanic dataset using the default setting for the support threshold, confidence threshold, and the maximum length. Okay, and we have in total 27 rules, and this is a small data set. As you can see, we only have 4 variables. Okay, so we have 27 rules, and the first rule, it has an empty set for the antecedent. It only has the adult as the right-hand side, as the consequent. Okay, so for these rules, it has the support is 95%. So that means 95% of the passengers are adults. Okay, and the confidence lived. So this rule is actually useless because you can see the left-hand side is actually empty. Okay, and also some other rules. So if you don't set the condition wisely, so you will have many rules comes out. This is a small data set. If you have thousands of items uh, and millions of baskets, so you will have many rules which are useless. So this is not good. So when you do the association rule mindings, so you have to select the those left hand side or right hand side and threshold wisely so that you will have a smaller number of rules to check. Okay, so here let's say in this data set we are interested in the survival status. Okay, so we want to see what type of passengers in the Titanic data set that have the relatively high survival rate, what type have relatively low survival. Okay, so this is our main interest. So if we focused on this, then we can easily limit our search to the part that we are interested in. So now this time I set the parameter is mean length is 2. So that means the minimum length for the rules has to be 2. So what does that mean? That means it has to be contain 2 items or more items in the right and left hand side combined. Okay, so in that way we will avoid those empty set. Why? Because here for the right hand side, that's the consequent, has to be either survival is no or survival is yes. So it has to be one of them to be the consequent. And the minimum length has to be 2. So that means the antecedent has to contain at least 1 item. So so we will not have this empty set because of the mean length is 2. Okay, and we restricted our search for the consequent is related to the survival status, either yes or no. Okay, and we set the support threshold to be 0.5%. Confidence level has to be 0.8 or higher. Okay, so in that case, we will have 12 rules. Okay, so you can see these 12 rules ordered by the lift size. You see the first one is second class, children, survived, yes. The support is 1.1%. And the confidence is 1. What does that mean? Remember the confidence? Confidence means given the class is second class children, all of them survived. So all the second class children are survived. Okay, so that's the confidence. And the lift is 3, so which is much bigger than 1. So that means there's a strong association. Okay, and the second is second class female children. Survived, yes, with the same confidence. Lift. And this one, you can see it's actually redundant. Why? Because the first rule already told us that all the children in the second class survived. And the second rule says all the female children in the second class survived, which is redundant, right? So you can see in the association rule mining, sometimes we can get those redundant rules. That means we don't have extra information provided. Why? Because you can see the that the left hand side is in the second rule is a superset of the left hand side for the first rule. Remember the superset? We talk about the superset here, right? So the superset, okay? So superset means that it is included. So this condition is actually included in this. So that's why we said the left-hand side for the rule 2 is a superset of rule 1. Okay? So these are the 12 rules. So we can eliminate those redundant rules, right? So I have these lines of code here to remove the redundant rules. Okay? You can check it after class. So I run this code and I found the rule 2, rule 4, rule 7, and 8. So these 4 rules are redundant. That means provides no extra information. Okay, so we can remove these rules. So now we have only 8 rules left. And these rules are related to the survival status. So the first 4 are related to the yes survival. So the next 4 related to the no survival. So you can see by looking at the lift, you can see one interesting thing is the rules for the survived yes has the lift value much larger than 1, right? But for the rules that found for the with the consequent is survival is no, not survived, is very close to 1. So that means what? So that means it's much easier to find those rules that indicates the passengers are survived. Okay, to identify those rules that indicate the passengers are not survived, which are lacks of those strengths, association strengths. Okay, so they are more like a random, and this is quite common in the association rule minings. It's much easier to identify one situation rather than the other. Okay, and here interpretation for the association rule mining results are very tricky. Sometimes we may misinterpret the rules. Okay, for example, for the survive is yes. Okay, so we only found those second class, right? So we have second class children survival rate is high. First class female survival rate is high, right? And second class female survival rate is high, right? So here, just by looking at the confidence, you can see 97% of the first-class female passengers survived. About 88% for the second-class female survived. About 87% of the female crew members survived. So nothing is about first-class children or third-class children, right? So this may give you some idea that maybe the survival rate for the first class and third class children are low because they didn't appear, right? So to investigate this issue, we can rerun the code by modifying the right-hand side to be survived is yes. Now we only consider the survived. Okay, so survived is yes, that's the for the consequent. But for the antecedent, we can have either first class, second class, third class, age is children, or age is adult only. Okay, so we lower the threshold for both support and confidence just to make sure we include all the rules. So we rerun this code, okay, and then we found 6 rules. So from these 6 rules, you can see the first one still about the second class children all survived. But look at the next one, first class children all survived because the confidence is 1, right? So why it didn't appear? The reason the first class children didn't appear is because the support is very low. That means only about 0.27%. Okay, so less than 0.3% of the passengers are the first class children. So because of the low support, it's below the threshold that we set first. Okay, so that's why it didn't appear. But it shows that all the first class children survived. Okay, and the first class adults, the survival rate is about 0.6. So about 62% of the adult first class passenger survived. Okay, well, and what about the second class adult? Survival rate is about what? It's about 1/3. Okay, so you can see the first class has a much higher survival rate for the adult passengers, right? So the second class has much lower. And what about the third class adults? Even lower, so less than a quarter of the third class adult passengers survived. But here there's a sad fact showing that for the third class children, the survival rate is as low as the second class adults, slightly lower. It's about only 1 out of 3 third class children in the Titanic survived, and 2/3 not survived. And actually, the support is quite high. Okay, support is over 1% in the passenger, but only 1/3 survived. So you can see when we do the association group minings, so you have to put the specific right-hand side or left-hand side based on your research interest. And sometimes if some rules that you expected to see didn't appear, that may be because of the threshold for the support or the confidence. So sometimes you need to lower the threshold or support for the support and lift and or the confidence so that you can see the results. Okay, and it is common that if you don't pay attention to this, you may misinterpret the association group mining results. Okay, so this is the association rule mining. Any questions? So this is the lab notes for the association rule minings. Mm. So this data set, I will go over this quickly, okay? Because we have another case study. And by the way, from next week, we will have our final project presentation. So make sure you prepare, and I will just randomly pick, okay? And if you want to volunteer to present on Tuesday, or if you want to present on Thursday, write me an email and I will put you on the list. Okay, so my intention is that this is a very good opportunity for you to practice your your presentation skills, which is very important, very critical for your career, right? So if you would like to take advantage of this chance, these opportunities, so just let me know and I will put your name down and I will ask those volunteers to present first. And also think about when I do the grading, I try to be as fair as possible. But if you don't present, you give me the report. And another student presents and also give me the report. So usually, although I'm trying to be fair, but if you present it, you can also add some more things in the talk, right? So you can have a better impression. So these are the things you need to consider. So I would recommend you, if you like to volunteer, don't wait. Just send me an email and I will let the volunteer to present on Tuesday and Thursday. These are very good opportunities. Okay. This is a data set from the UCI machine learning repository. Originally, this is a regression problem. So this from the census data, we have 14 predictors. Some of them are categorical, some of them are numeric. And the target variable is the income. It's numeric. But now here, I change this income to the binary categorical variables. So we set the 50,000 at the threshold. If it's above, we say high income. Below, it's low income. So we want to find out the rules that is showing the income status. Okay, so this is a good practice that we can use to do the association rule mining on a real data set. Okay, so here, this is the description of the data set. So we have these 14 predictors and the target is the income. That's the last one. Okay. But for these 14 predictors, some of them are numeric, some of them are categorical. But among them, two of them are useless. One is the education number. So this one is exactly the same as education, which is just to represent the education through the numbers. Okay, so that's why I will remove this variable. And also this one is the weight for the census data. Okay, these weight are given by the designer of this survey studies. Okay, so this is not related to the our response. variable. So we will just remove this one and this one. Okay, so after we removed these two variables, we have 4 numeric variables. These 4 numeric variables are the age, hours per week, and capital gain and the capital loss. So these are the 4 numeric variables. The rest of the variables are all categorical. Okay, and we know that for the association rule minings, these conditions are categorical variables. So we need to categorize those numeric variables into some categories. Okay, so before we do the association rule mining, we need to change these numeric variables into categorical variables. So these are the sample code. And here for the age, I used a cut function in the R, an ordered function. So here I put the age into 4 categories. Okay, so the threshold are the 25. So if it's this 15 is the youngest age in the data set. Okay, but the cut is at 25. So if it's between 15 and 25, we call it young. 25 to 45, middle age. 45 to 65, senior. 65 and above. 100 is the highest age. So it's called old. So this now age becomes a categorical variable with young, middle age, senior, and old. Okay. For the hours per week, in this data set, we have the lowest value is 0 hours per week to the 168 hours per week. Okay, so that's huge. So, so we put them into 4 categories. If it's between 0 and 25, we call it part-time. Between 25 to 40, full-time. 40 to 60, overtime. 60 and above, workaholic. Okay. So for the capital gain, we ordered into 3 levels. If the capital gain is negative or 0, then we say it's none. Okay. If it's from 0 to the median of the capital gain, then we call it low. If it's above the median, we call it high. And similarly, we apply to the capital loss. Okay, so after these steps, now we have all the variables as a categorical variable. Okay, so then we have to do one more step before we can do the association rule mining. That is the AS by this data set's name, and then transaction. So what does that mean? So this line just recoded this data set as a transaction data set. Okay, so what does that mean? That means after this step, now this becomes a transactional data set with how many columns? We have about 48,000 rows. So that's the 48,000 responses from the surveys. But how many columns? We now have 115 columns. Why it's 115? Remember, we have 12 variables, 12 predictors, right? Because we originally we have 14, but we removed 2, so we have 12. But why this becomes 115? Because we dumbify these variables. We do it as a market basket analysis. So every column is binary. Okay, so for example, for the age, instead of having just one variable as age, now how many variables do we have? we have 4 variables, right? We have 1 dummy variable for the young, 1 dummy variable for the middle age, 1 dummy variable for the senior, 1 dummy variable for the old. So that's why it has 115 columns. Now, each column is a binary variable, okay? So make sure you understand that. So now this is a transaction database. Now we can apply the association rule minings. So this is the summary of the data set. And then we can run the item frequency plot to show those frequent items. Okay, so these are the frequent items. And then we can apply the a priori algorithms. Okay, so we have, where's the code? Here, we apply the a priori on the adult data set. So we set the threshold for the support to be 1%, confidence to be 60%. Okay, and we have about 276,000 rules. Okay, and this is the summary of the rules. Okay, so these are the, now there are so many rules, there's no way we can examine all of them. As I said, you have to read, you have to narrow down the consequent set or the antecedent set, right? So here we are focusing on what? We are focusing on identifying the subpopulation that tends to have the high income and the low income, right? So that's why we focused on the right-hand side to be the income is small or income is large. And also we can set some threshold on the left. Okay, so, and we don't have to redo the rules, rerun the a priori algorithms. We can just use the subset function to find out the subset of rules. And these rules contains over 276,000 rules. So we want to find the subset of these rules such that the consequence is about the income status. Okay, so now we have these are the rules for the low income group. These are the rules for the high income group. Okay, so for the low income group, we have, these are the leading rules. Okay, sorted by the confidence. Okay, so you can see these are the rules that is related to the low income. Okay, and these are the rules related to the high incomes. And look at the lift values. So the lift value for the high income group is 4.2 something, right? But for the low income, the leading ones are 1.4. So you can see that's the asymmetry that I mentioned, just like in the Titanic, okay? So it's easier to find those rules that is closely connected to the high income group. So it's easy to identify those high income group compared to the low income group, okay, by looking at the lift values. And the next part for this lab notes is this is very useful in the associated group minings, is the subsampling. Why we need to do the subsamplings? Because nowadays, if you use this technique to some real data, okay, and for the real data, for those transactional data set, it usually contains like billions of transactions and 10,000, 100,000 of items. Okay, like if you want to do it, apply to some transactional database from Amazon, Walmart. So these are huge data sets. And there's no way we can run this on a personal computer. So even on a supercomputer, because of the large sample size and high dimensions, the computation efficiency is very low. It takes hours, days to find out all these rules, right? So subsampling is a very useful technique in the association rule mining such that we can substantially reduce the computing times through do the association rule mining on a subset, a random subset of database. Okay, so here there are several formulas related to the subsampling sample size. Okay, so here I'm choosing the one that is the easiest one. Okay, so this was proposed by Zakis and others. So in 1997. Okay, so here they show that for an item set X with support level to be here is tall and an acceptable relative error of support epsilon at a given confidence level 1 minus C. Okay, so what does that mean? So that means, let's say 90% of the confidence for the relative error rate for the support is around, let's say 5% or 10%. Okay, so then the needed sample size can be computed by this formula. Okay, so in our case, remember the sample size, we have about 48,000, right? We have how many? We have I think we have 48. Yeah, over 48,000. So here, let's apply these formulas, and we set the relative error rates for the support is 10%, and we set the minimum support threshold to be 5%. Okay, so the confidence level to be 90%. So the confidence level is 90%, that means C is what? C is 1 minus C is 90%, that means C is 0.1. So C is 0.1, and the relative error rate, an acceptable relative error rate is 0.1, that means it's 10%. And our support threshold is 0.05. So the tau is 0.05. Okay, so by using that, we calculated, and you can see the sample size is, the minimum sample size is 9,211. Okay, so this is the minimum sample size. You should round up, okay? So instead of searching, using all the 48,000, we only need to use 9,000, about 9,000. Okay, so that's a very big change, right? So we only have less than 10,000 subject sample. And this plot shows the item frequencies. Okay, the bar shows the item frequencies from the population, while those lines, connected lines, these shows the frequency level, the proportion for each frequent items based on the samples, random sample based on this, about 9,211 random samples. So you can see the proportion based on the true whole data set and a subset are very close. Okay, so this plot shows the ratio for the lift. I'm sorry, shows the lift ratio for each items, which is the support, or which is the proportion based on the samples over proportion based on the populations. So if they are exactly the same, the lift ratio should be 1. Okay, if the sample proportion is lower than the population proportion, then it will be lower than 1. If it's greater than the population proportion, then it will be greater than 1. Otherwise, less than 1 or equal. Okay, so here you can see for these frequent items, the lift ratio is around 1. one is exactly so is accurate estimate, right? So you can see some of these are a little bit above, some of these a little bit below, but most of them are within 5%, right? 5%. Okay, and look at these here. I highlighted these two. Why I highlight? So this is the work class is local government. It has a quite large ratio. So that means there is a quite large difference, relatively speaking. Okay, about over 4% difference. But this one has a very low difference. That's the work class is private. So I want to show you why these two have a big difference. Okay, it's not by random. It's not. So what is the reason why these two have big ratio difference? One is has over 4% of deviate from the. So that means the sample proportion are 4%, over 4% larger than the true proportion. While this one for the private class are very close. These two are very close. Okay, so the reason is if you look at these two, look at the frequency, look at the proportions. The reason these two, this one local government has high deviation from the true proportion is because of the this class has low proportion. Does that make sense? Because this class has low proportion, so that's why if compared to the true proportion, it tends to be have a relatively high error rate. Okay, but this one has low error rate because this one has high proportions. Okay, so that means if you have a small sample size, of course the error rate will be high. If you have large sample size, of course the error rate will be low. Okay, just like that. And the next is just compare the frequency, compare the item frequencies between the sample from the based on the random samples and based on the whole data set. Okay, and we can see that the agreement are very good. Okay, so you can see here the agreement. I use the match function. So almost all the frequent item set were found in the sample from the random samples. So in other words, we have many frequent set found by using the entire data set. Okay, and the about 98 of these frequent item sets found from the using the whole data set were also found by using 9,000 random samples. Okay, so instead of using the whole data set, we just used a random subset, and we recovered about 98% of these frequent item set. Okay, so you can see that means it has a good agreement. Okay, and what are those item set that are missed? Right, so here I'm doing a check on those items that are missed. So this exclamation mark means it's not matched. Okay, so I'm focusing on those item set that are not matched between the frequency item set found by the samples found by the whole data set. So what are those mismatch come from? And look at these support levels. You can see the minimum to the maximum is around 0.05. Even the maximum is very close to 0.05. Okay, so what is 0.05? So that is actually the minimum subset, is the support threshold I set here. So that means since we set the threshold, support threshold at 0.05, those missed frequency item set are mostly from those item set that has the support level which is very close to the boundaries. Okay, so this is what we missed. But if it's way above this, we will not miss it. Okay, so, and this shows the computing times. Using the full data set, we have, on my machine, it has 0.28 seconds. And if I use the samples, 0.06 seconds. So what is the speed up rate? Speed up rate is 0.28 over 0.06 is about 5. So the computation efficiency has been improved by a lot, by 5 times about. Okay, and don't think this is 0.28 is negligible, but this is a toy set. This is a very small sample size, 48,000. As I said, if you change to billions of transactions, millions, 100,000 of items, the computation time will be days, weeks. Okay, if you can improve the computations by 5 times, 10 times, that's a lot. Okay, so that's why in practice, almost all the real studies, people use the subsampling. And if you use the subsamplings, this is a good formula to use to give you some guidance about the minimum sample size that you have to use. Okay, any questions about this study? Okay, if you don't have any questions, we will move to our last topic. So this is the second case study in the data mining. So this the first case study, we focused on the pre-processing the data sets and data cleaning. But for this one, I will put more time on interpreting the results. Okay. So this study is from the Kaggle's 2012 data mining competitions. So the purpose for this study is to predict whether a commentary posted during a public discussion is considered to be insulting to one of the participants. Okay, so the response is binary. Either 0, that means it's a neutral comment, or 1, that means it's an insulting comment. But here there are some more explanations on what is insulting, okay, and what is a neutral comment. So looking for the comments that are intended to be insulting to a person who is part of this blog, forum conversations. So we are not looking for the insults directed to non-participants, such as celebrity, public figures. Okay, so insults could contain in different ways. Okay, and the comments which contains profanities or racial slurs but are not necessarily insulting to another person will be considered as neutral comments. So these are some more explanations on what is how to define a comment is neutral and insulting. Okay, it is insulting only that targets to one of the participants in this discussion forum. So the predictors are the Unicode escape text of comments. So this is a text mining. Okay, so the content is mostly English language comments, but with some occasional formattings. So here I'm listing a few examples. So those examples, those comments are in the left column. Right column is the response. Okay, so you can see this is a text mining example, and it's not an easy data set. Okay, so we have to pre-process this data as a text mining problem, and also we need to reduce the dimensions. Okay, and we will see that in a minute. So the outline first is data pre-processing. So the purpose for this step is to use the frequency of commonly used words as predictors. And we remove those rarely used words, numbers, white space, punctuation marks. Okay? So we only keep those words that are commonly used. If like just there's a word only one or two commentary use that, we will remove that because this is not a common word. So, and also those irrelevant informations like the white space, numbers, and punctuation marks, we just removed. Okay, and then the next step is verbal screening. Why we need to do that? So after the pre-processing, after the first step, and you will see in a minute that we have over 20,000 words in left. Okay, so these are the over 20,000 predictors. This is way too high, right? So that we need to reduce the dimensionalities so that we can apply some predictive machine learning algorithms on this data set. Okay, so the purpose is to further screening away those irrelevant or infrequent words that reduce dimension to less than 1,000. Okay, after this step, the step 3, we will build predictive models. And we mainly focus on the classification tree and the random forest. Okay, and also we will do the interpretations. And the last one is we will also apply it for the market basket analysis. So we are looking for some insult related terms and non-insult terms. And we will check these terms and confidence and the lift value. Okay, so let's see. So the first is pre-processing. So we will remove those extra white space. Like here, there are extra white space between the I and like and database and after database. So we will just remove these extra white space and also change the uppercase to lowercase, remove the punctuation marks, and also we will remove those stop words. So what are the stop words? Stop words are those extremely common words which provides almost no value or very little value in the text mining tasks. So what are the stop words like about, above, across, and, both, but, can, I? So these are the stop words which used very commonly, but usually it doesn't have any discriminating power in the text mining tasks. Okay, so we will also remove these stop words, and also we will stemming the words. So stemming the words is a very routine step. So it will reduce those inflected words such as change the past tense to the current tense. So we will have the walked change to walk, and the plurals change to singulars. Okay, so like that. And after these steps, we will have a document term matrix. Okay, for example, we have two documents, and the document term matrix will be I, like, hate, database. So for the first document, we will have 1101. For the second document, we will have 1011, like that. Okay, so that's the output after the first step. Okay, so to do this, we don't have to do it by hand. There are packages available in R, and there are many text mining packages available. So here I'm using the TM library in R. So TM is is a standard text mining package in R. So we can remove those white space like here. This step is to remove the white space. This is to change the uppercase to the lowercase. and remove the punctuation marks, and remove the stop words, and remove the numbers, and stemming the words. So all these are available. So I'm just writing a function and apply this function to the data set. Okay, so after all these steps, we have, this is our training set. So for the training set, we have 4,615 commentaries. And we have how many words? After doing these steps, we will have over 20,000 words. Okay, so that's the first step, pre-processing. And after that, we go to the second step to further screening away those words. So this time we are focusing on those rare words. So for these, what does that mean? Rare words. So here, I'm just showing you an example. So we want to have the word has to appear at least 14 comments, in at least 14 comments, which is about, there's a typo, 0.3%, not 0.4, 0.3% of the training data. Okay, so we want the words that we kept has to be appeared in at least 14 comments. That means it's about 0.3% of the total commentaries in the training set. Okay, so that's how we defined frequent word. Below that threshold, rare word. So we just remove those rare words. Okay, so by doing that, we have about 800 words left. Okay, so you can see the dimensionality shrinks. Okay, but we need to do some further filtering. Why? Because some of the words, although appeared quite commonly, but has no discriminating power to identify the comment is neutral or insulting. So we should remove these words, right? So how do we find these words? This is a categorical data analysis, okay? So we want to find those words that has the discriminant power or is associated with the insulting status, right? So this is a chi-square test, okay? So think about, let's say, here I'm showing an example. So absolutely, this is a word, okay? So we have two conditions. So one is that the document contains the absolutely, okay? And this one is no absolutely. So this that means the document does not contain absolutely this word, okay? And then we show the insulting status. So this one is insulting, and this one is neutral. Okay, so then we have a table. Okay, so you can see these are the tables that showed here. Okay, so for this table, then we can run the chi-square test to see if the appearance of this word absolutely is closely connected, strongly associated with the insulting status. And here you can see there's no clear association. Why? How can I see that? Look at the ratios. So what is the ratio between these two? It's about 1 times and 3 times. Is that right? So we have about 1/4 of the document that contains absolutely. No. 1/4 of the documents that are insulting. 3/4 are neutral. Okay, and these we have 26 documents contains absolutely. But look at the ratio for the number of documents in the insulting and the neutrals. The ratio is still like a 1:3. Is Is that right? So the ratio for this one, 1,200 is about 1/3 of the 3,300. And look at the ratio for this, 20 and 6 is about 1 and 3. So you can see the proportion doesn't change much, right? So you can see the percentage of the documents that contains absolutely this word in the insulting commentary and in the neutral commentary are about the same. So that means there's no strong association between the insulting status and appearance of the absolutely this word. And you can see the chi-square p-value is 0.87. That means the these two appearance of absolutely and the insulting status, these two are independent. No association. So that means this word has no discriminating power. Right? On the other hand, let's see another word, moron. Okay? So you can see there are about 67 documents in the training set contains moron. And most of them appeared in the insulting. But insulting only contains about 1/4 of the total. But most of them in the insulting. So that means there's a strong connection. So those morons words are mostly appeared in the insulting comments. So that means there's an association, strong association. Okay, and you can see the p-value is highly significant. So you can see by using the chi-square test, we can easily identify those words that is related to the insulting status or not. Okay, and here I'm just running a chi-square test on all the all the 800 words after the first two steps, and I use the threshold at 0.1 at the p-values. So if the p-value is no greater than 0.1, we will keep these words. That means they have some association. So they show some information about the insulting status. Okay, so here I'm just listing the top 70 terms. And you can see easily these terms are very obvious related to the insulting status, right? So after this step, we have 254 terms left. So you can see the dimensionality becomes much lower. Now we can apply some predictive algorithms. Okay, so here I'm using two predictive algorithms. One is random forest, and one is the classification trees. Okay, so for the random forest, I applied on the training set, which contains about 4,600 commentaries. For the test set, about 2,000. Okay, so here the default M-try value is 15, but I used out-of-bag error rate to select the optimal value. So here the optimal value is around 3 and 5. Okay, so why? Why in this one the optimal value is much smaller than the default value? Because here in this data set, you will see that these words are kind of independent, but they all showed some information about insulting status. Some sentence, some commentary use some of the words, but not all of them, right? So each word shows some information. So it's very diverse. Okay, so what is the best strategy to create this ensemble? The best strategy to create this ensemble is to use all of them. Is that right? So that's why the M-tree value should be low. Why? Because if we have a low value for the M-tree in the random forest, then all these trees will be very diversified, will be very different, will be very independent. Some of the trees focus on these few words. Some of the trees focus on the other set of words. Okay, in that way, we have a better ensemble. But if we set the M tree to be large, then all the trees are similar. They are all used just a small set of these words. Then it's no good. Why? Because it's not diversified. Okay, so that's the reason. And here the AUC scores is about 0.76, and the miss rate is about 18.9%. So the classification results are not very impressive. Usually the AUC score with usually people considered a good prediction performance with the AUC score greater than 80%. Okay, so that's a rule of thumb. So, and but here it's below the 80%, and misclassification rate is also quite high. But still, it shows some uh, reasonable performance, and we will go back to this point in a minute. So compare these results with the screen data with about 800 terms left. Okay, so these are the results based on based on these 254 terms. Okay, so the 794 terms are without using the chi-square. Okay, so if we use all the 794 or 93 terms without doing the chi-square, and we run the random forest, still the M tree optimal value is around 5. Okay, but the computing time increased a lot from 71 seconds to 572 seconds. So you can see the computation becomes much slower, right? Because the dimensionality increase. But the AUC score is actually 0.77, which is almost the same as this one. And the miss rate actually is slightly higher than the miss rate here. So you can see there's basically no improvement, but just wasting lots of time. So you can see the benefit of doing that, filtering away those irrelevant words. We can improve the computations efficiencies. We can also get competitive results. Okay, and these are the AUC's ROC plot, and this shows the relative importance plot. Okay, so you can see the most important. So these are the first top most important variables. So you can by looking at these words, you see these are really related to the insulting status, right? Okay, so this is the second approach. We use the classification trees, and you can see the results is actually AUC score is about 0.73, which is slightly lower than the random forest. Okay, so the random forest is about 0.76, but this is 7.73. Okay, so and the miss rate is about 24 or 22 based on how many predictor do we use. This one is based on the about 200 something after the filtering away those irrelevant through the chi-square test. But without eliminating those irrelevant through the chi-square test, we run the classification tree. The miss rate is is about a quarter, so it's worse. Okay, this is very similar to the random forest, and AUC scores is about 0.73. This is the tree diagram 1. This is the tree diagram 2. So you can see these trees also use these words to do the classifications. Okay, and these words actually agree with those selected words. Okay, now the last part is the market basket analysis. So I also run the MBA here because I want to find out those rules. That means here in this study is those bag of words that can identify the insulting status. Okay, so I use the a priori and I set the minimal length to be 2 to avoid the empty set for the left hand side. The minimum support threshold is 0.002. The confidence threshold is 0.7. Max length is also 2. So that means the length has to be 2. Okay, and the results, so the right hand side is insulting equals yes. Okay, so by running this, you can see we found this bag of words that has the highest confidence levels sorted by the confidence. Okay, and I do the same thing. Now this time I target to the neutral comments. So the right hand side is insult equals to no. And you can see these are the lift values. And you can see the lift values are much smaller for the neutral comments compared to the insulting comments. So this asymmetry always exists in the Titanic data set, in the survey data set, and also in here. So after running these steps, okay, now I'm trying to show you an example of how do we do the discussions, how do we analyze the results. Okay, so before that, these are just running some programs. So here, we know that the misclassification rate is not impressive at all, right? So after all these studies, we found AUC scores not close to 1. Misclassification rate is around 20%. It seems like this is not a good study. We don't have a very good results, but that doesn't mean we cannot tell anything. Okay, we can still find something interesting. So here I'm focusing on maybe we can look at those errors that we made. So there are 2 types of errors. Is that right? So we have either the false positive or the false negative error. Okay, so what is false positive? False positive. So here means positive means that it's the insulting commentary. False positive means what? Means we predict those commentaries are insulting, but actually they are neutral. So that's what we call it false positive. Okay, so we need to find those why we make false positive errors. Okay, so here I'm focusing on those because random forest gives the best prediction results, relatively the best. So look at the random forest results. I'm focusing on those samples that with the probability of being the insulting to be over 0.9. So from the random forest eye, from the eye of the random forest classifiers, we have 90% of over 90% of chance that commentary is insulting. But the real world label is it's actually neutral. Okay, so I want to select those mistakes that I made. Okay, so I found these are the mistakes, these are the samples that I made these false positive. So all these samples in the random forest, they predict they all have over 90% of chance to be insulting, but actually they are all neutral. Then I look at these comments. Okay. And then I can, after I take a close look of these comments, I can find out why we made this mistake, why random forest made this mistake. Okay, so I found that for those false positive errors, I found three main reasons that those classifiers made. Okay, so first reason is insults direct to the non-participants, like celebrities, public figures. So in this case, a random forest doesn't do a good job to distinguish the insulting is directed to a participant or directing to a non-participant. So I listed some examples here. Okay, and another main reason is some of the comments they use other language instead of English. Okay, so that also makes the random forest give the wrong warning message. Okay, so and the last one is to use the word with its implicit meanings. Okay, so that's another reason. And the next is I can also focus on those false negative errors. What is the false negative error? False negative errors means that from the eye of the random forest classifier, it's a non-insulting. It's almost sure it's a non-insulting comment, but actually it's an insulting comment. Okay, so that's the false negative errors. So similarly, I said I found those. I'm trying to find those mistakes with from the random forest eye. The chance of being insulting is less than 2%. That means we are almost certain this is non-insulting from the random forest eye. But actually, it's insulting. Okay, so I found these 20 examples that I made mistakes from the random forest classifier. Okay, then I look at these, found what are the main reasons. So first is some of them use the infrequent, so relatively infrequent words. Okay, and some of them use misspelled words. So that is another main reason. And the other one is use the punctuation marks and symbols. And the last one is to use the implicit meanings. Okay, so these are the main reasons why make those false negative errors. So I want to show you some examples. Even though the classification results may not be good, we can still do something, right? We can still find something out of it, okay, which could be useful, which maybe we can, that can give us some evidence, can give us some idea that we can further improve our models, okay? And the next is we also need to treat ourselves as a PI, the principal investigator for this project. So as I said many times, as a statistician, you have to be actively involved in this. Okay, you should not treat yourself as a programmer, instead an investigator. Okay, so here, based on all these results, okay, so we see that the prediction accuracy is not satisfying, and the main reason is that the specificity is high, but the sensitivity is too low. Okay, so here I'm showing the sensitivity and the specificity based on the random forest classifier results with the using the 254 terms. That means after the filter those irrelevant through the chi-square test. So you can see the sensitivity is only 38%, while the specificity is over 96%. Okay, so what does that mean? So that means here in this study, for those insulting comments, we missed lots of insulting comments, and we predict those insulting comments as the neutral comments. Okay, but for the specificity is high means that for those neutral comments, actually we predict most of them as neutral comments. So that's why the specificity is high. So that means it's difficult to identify those insulting comments. Okay, while it's relatively easy to identify those non-insulting. Okay, so compared to the random forest, CART achieves a comparably predictive accuracy with a highly interpretable tree diagram. And also based on the market basket analysis, we also find a list of insulting terms. Although we found a list of non-insulting terms, but they have low lift values, which are almost independent. So after all, I would like to suggest to have an alternative to building predictive models. Instead, we can set a term policies or a filters. So based on the random forest, CART, and MBA's results, I found these 24 terms as the insulting terms. Okay, so these are based on the random forest relative variable importance plot, and the CART splitting variables, and also the MBA's results. So these are the bag of words that appeared in at least two out of these three methods. Okay, so the odds of being an insulting comment, which include at least one of these 24 terms, is 1.27, while the odds of being an insulting does not include this is only 0.189. So that means the odds ratio is 6.72. Okay, so what does that mean? So that means the chance of a commentary being an insulting that includes these words, at least one of these 24 words, is much, much higher than the chance of a commentary does not include these words. And the ratio is over 6.7 times. And these 24 words, if we look at all these insulting comments, more than half of these insulting comments include at least one of these 24 terms. So this can give a very simple but effective approach as an alternative to a predictive models. So we can use this as like a term policy or the filters to filter away those insulting comments. Because it's simple, we only have these 24 terms. Its effectiveness, the odds ratio is much higher. So that means the discriminating power based on these 24 words are almost 7 times higher than the comments without this. Okay, and also it includes over 50% of the comments. Okay, so that shows an alternative approach. So what do we learn from this case study? First is data management is very important, data processing very important. And next is sometimes if we have very high dimensions, we also need to consider the variable screenings to reduce the dimensionality to a manageable size. Then the third one is modeling. So data mining is not just throwing some data set into some models that you know and let it go. Okay, so we have to choose the model wisely. So here I didn't mention why I choose the trees and random forest. because here the trees and random forest, they are both based on the trees, right? So the trees are the local method where the sample models are fitted on a neighborhood. So the tree can pick up the variables, can select the variables automatically, okay? And also tree is computationally efficient, so there and interpretable. So there are some very good reasons here why I choose the tree and the random forest, okay? And not just prediction, interpretation and the knowledge discovery also very important. Like here, we are not just showing the AUC scores. We are not just showing the misclassification rate. We can also show like the bag of words that is closely related to the insulting and the neutral comments, right? So these are the actuals from the prediction, but they are very important. Actually, most of the time, they are more important than just the prediction results. And also suggestions and conclusions. So think yourself as an investigator, not as a program. Okay, so these are what you should learn from this case study. Okay, so for next week, we will have the final presentations. Any questions before we dismiss? Okay, let's stop here.